guys, welcome back to this channel. Nice to see everyone again. And for today's video, we'll talk about topic 7.2, molecular shape. And in this part of video, we are going to discuss two things. The first one is your VSEPR theory, VSEPR theory. The second is a bit of drawing, basic molecular geometry. Kind reminder over here, we'll be drawing a lot of Lewis structure. So if you are not good in drawing your Lewis structure yet, please proceed to the previous video first. Please watch the 7.1 part 2 on how to draw Lewis structure. Alright, so let's start. So what is actually VSEPR theory? VSEPR represents valence shell electron pair repulsion theory. And what is so important about this theory? This theory is going to tell you that the electron pair in the valence shell will repel each other and arrange as far as possible to minimize the repulsion. First and foremost, why the electron pair will repel each other? Simple guys, because the electron pair will be in negative charge. When the electron is in negative and negative charge, negative and negative will repel each other. So when they repel each other, they will be moving far from each other and they will try to arrange as far as they can so that the repulsion will be minimized. That is what VSEPR theory is about. And we have three types of repulsion. We have lone pair repulsion, which is the strongest repulsion. We have lone pair bonding pair repulsion. And last but not least, the weakest repulsion is your bonding pair repulsion. What is actually lone pair repulsion, lone pair bonding pair repulsion, and bonding pair repulsion? If you remember previously when we draw Lewis structure, we might have something like this, like your water molecule, where you have two lone pair on the oxygen. So when you have two lone pair over here, this lone pair will give rise to a lone pair repulsion. Okay? Or another type of example that I have that we draw before is your PCl3 in your Lewis structure where we have a lone pair over here. And then this lone pair and this bonding will give rise to a lone pair bonding pair repulsion. So when a lone pair repulsion, you need to have minimum two lone pair in your molecule. So for the lone pair bonding pair, you need to have at least one lone pair in your central atom and then you have a bonding. So lone pair bonding pair repulsion. Last but not least, bonding pair repulsion means in your molecule, you only have bonding pair, you don't have any lone pair. For example, you have your CH4 over here. So in your CH4, there is no lone pair on the carbon, you only have bonding pair in the structure. So you have your bonding pair repulsion. So that is what we mean by lone pair repulsion. Lone pair bonding pair repulsion and also bonding pair repulsion. It depends on your Lewis structure. Therefore, it's very important to know how to draw the Lewis structure before proceed. Okay? And next, basic molecular geometry. And in your syllabus, we have 5 basic molecular geometry. First and foremost, we have linear. Second, we have trigonal planar. Third, we have tetrahedral. Fourth, we have trigonal bipyramidal. Fifth, we have octahedral. Next, let's start with linear. So, we are going to look into a few things. General formula, number of electron pair, molecular geometry, and bond angle. So, your general formula of linear will be AX2. What is meant by AX2? Your A is your central atom, means that your A will be bonded to your X, will be bonded to your X. The number of electron pair for linear will be 2. The molecular geometry will look something like this. You have your central atom, that is your A, that is your X, that is your X. So that is your molecular geometry should look like. And what do you think the bond angle will be? Bond angle. So it's the angle between the bond. And since it's a linear, therefore the bond angle will be 180. And the bond angle over here is 180 for linear. Okay, don't worry, in the exam you do not need to draw a 3D. I will show you how to draw in your exam. Let's do an example for linear. The example I have for linear is BeCl2. So if the question starts off with a molecule like this, alright, how do we know what would be the basic molecular geometry? Simple. We will start off with drawing the Lewis structure first. Means we will start off with total valence electron. Okay, you need to draw a correct Lewis structure before you can determine the molecular shape. So the total valence electron, beryllium, 2, chlorine, 7 times 2. So we have 14 over here. Because 7 valence electron times 2, we have learned that in your previous video. So that will give rise to a total valence electron of 16. And the step 1 in drawing your Lewis structure is your central atom and your skeletal structure with a single bond. So beryllium as a central atom, skeletal with chlorine, chlorine. 2 single bond, so I used up 4 electron already. 16 minus 4, I left 12 electron. The next step after you minus out the electron, we need to make sure your terminal atom is octet. So your terminal atom, chlorine, need to achieve octet. Alright, how to achieve octet? We already have a bonding with 2 electrons. Each chlorine need another 6 electrons. So we put them in the form of pair. So I give them 3 lone pair. Remember what is lone pair? Lone pair is the pair of electron that does not involve in the bonding. So I have put in 6 electrons each in the chlorine. So I have put in 12 electrons in total. Therefore, your total valence electron now is 0. You are done with the total valence electron. But we are not sure whether our Lewis structure is correct or not. So make sure you check them whether they achieve octet, incomplete octet, expanded octet, or odd number octet. So my terminal atom both are octet. My beryllium is an incomplete octet. Beryllium having 4 electron around it, okay, 2 plus 2 in the bonding. So beryllium right now is an incomplete octet. Why beryllium can be an incomplete octet? Because in your syllabus, there is only 3% can be incomplete octet. Beryllium, boron, or aluminium can be incomplete octet. Since your beryllium can be incomplete octet and chlorine is now octet, therefore this is the correct Lewis structure. And from this Lewis structure, how can we determine the molecular geometry or the basic molecular geometry? We are going to calculate the electron pair around the central atom. We will focus only on your central atom. How can I calculate the electron pair? We have a formula over here, very simple. Bonding pair plus lone pair. But the bonding pair, we will only take count of sigma. Okay? If you have a single bond, it's a sigma bond. If you have a double bond, then it will be a sigma and pi. Bear that in mind. So, all that is a single bond. So, that is your sigma, that is your sigma. So, your electron pair for this molecule will be 2 sigma plus 0 lone pair. Because around your central atom, there is no lone pair. Therefore, your electron pair is 2. And based on your electron pair is 2, you know that your basic molecular geometry will be linear because electron pair is 2. So since your basic molecular geometry is linear, then we need to draw this again and to make sure they must be in the shape of linear. So your beryllium, straight line, the bonding must be straight because linear having a bond angle of 180. Okay, you need to redraw your Lewis structure in the correct geometry. Show the geometry of linear look like what? And from this drawing, you know that your bond angle will then be 180. The 180 is from the bond to the bond. Okay? So how can we determine the basic geometry? The basic geometry will depend on the electron pair. How can we calculate the electron pair? The formula is the bonding pair plus lone pair. Bear that in mind, bonding pair we only take count of sigma. But where do we get this bonding pair and lone pair from? The bonding pair and lone pair will depend on your Lewis structure. Alright? That's why I say if you cannot draw your Lewis structure, you better don't proceed with this video. Go back and learn how to draw your Lewis structure before you learn on how to determine the basic geometry. Okay? And that is how we determine the basic geometry if the question gives you a molecule. Next, let's proceed with the second basic geometry, which is trigonal planar. Trigonal planar, same thing, we will look into a few of it. Trigonal planar, the general formula is AX3. Okay, it means that the A is your central atom, will be bonded to 3x. That is what we mean by your AX3. The number of electron pair over here will be 3. For trigonal planar, the number of electron pair is 3. So your molecular geometry will look something like this. Alright, that is my A, that is my X, and if you look at it, it's a triangle on the plane because it's a trigonal planar, so it will be sitting on the plane. Therefore, you have 360 divided 3. Every bond angle over here is 120 degree. So the bond angle will be 120 degree for trigonal planar. And that is all about trigonal planar that you need to know. And let's do an example for trigonal planar. I have BF3 over here. Same thing. Remember, before we can determine the basic geometry, we must have the correct Lewis structure. So start off with the Lewis structure with total valence electron. Total valence electron for boron, 3. For fluorine is 7 times 3. So I have 21. Total electron, I have 24 over here. So I'll start off with my BF3 in a skeletal structure and single bond. So 3 single bond minus 6 electron and 18 electron left. So 18 electron left over here. The next step, what do we do after you have your skeletal structure and you minus out the single bond electron? We will try to octet all your terminal atom. So my terminal atom over here is my fluorine. We are going to octet the fluorine by giving them 3 lone pair. Why 3 lone pair? Because every single fluorine already holding a bonding pair that have 2 electrons, a single bond that have 2 electrons. So every fluorine is now need another 6 electron to achieve octet. That equivalent to 3 lone pair. So you have put in how many electron in total? 6 electron each times 3 minus 18. So you are done with the total valence electron. And before you make sure your Lewis structure is correct, we check the octet. So your F right now achieve octet because everybody now holding 8 electron. So your boron having 6 electron around it, incomplete octet. So is your boron qualified to be incomplete octet? Yes, incomplete octet is included boron. So this Lewis structure is correct. After your Lewis structure is correct, we can proceed to calculate the electron pair and also determine the basic geometry. So your electron pair over here, again, the electron pair, we will focus only on your central atom. Okay, we will focus only on your central atom. Electron pair will be bonding pair that we take count of sigma only plus lone pair. So the electron pair for central atom, the bonding pair is 3. You have 3 bonding pair, 1 bonding pair, 2 bonding pair, 3 bonding pair. 3 bonding pair and no lone pair, 0. So the bonding pair right now is 3. If the bonding pair is 3, what would be the basic geometry? Alright, if the bonding pair is 3, the basic geometry will be trigonal planar. Alright, how should a trigonal planar look like in a 2D? How can we draw it out? Simple. Your central atom, boron. Trigonal planar means we are going to draw a trigonal. Alright, 1, 2, 3. Okay, can you see a trigonal over here? Okay, that is your trigonal planar. Put in your F and their lone pair. Why do we have this shape rather than just something like this? Alright, because your VSEPR theory, your VSEPR theory, which is the valence shell electron pair repulsion. Your bonding over here that holding the electron, alright, all this bonding holding electron, that will repel each other, that will have repulsion. So what happens when they have repulsion? They will try to move far away from each other to minimize the repulsion. So the furthest that they can go is all 3 of them will be staying 120 degrees away from each other. Because in one circle is 360, I have 3 of them. The maximum I can go is 120 degree. And that will give rise to your bond angle of your trigonal planar, 120 degrees. Okay? All this basic geometry shape is produced because of the VSEPR theory, because of the repulsion between the bonding pair. So the repulsion, all the bonds tend to move far away from each other. So when they move, they will change the shape. That is how the shape come out. Okay? Proceed with the third basic geometry. The third basic geometry that we have is tetrahedral. So what is about tetrahedral? The general formula, you can guess it actually. We are moving from AX2 to AX3, and now we are moving from AX4. AX4 means what? Means that your A and X will be arranged in the form of tetrahedral. That is how your tetrahedral look like. The number of electron pair over here similar. If just now AX2, number of electron pair is 2. General formula AX3, number of electron pair is 3. So if my general formula is AX4, my number of electron pair will be 4. So if the number of electron pair calculated is 4, then it will be a tetrahedral. The molecular geometry looks something like this. It's like your chicken leg, it's like your chicken leg. So this is how it looks like in your 3D. It's like your chicken leg. And the bond angle between them, all of these bond angle are the same. Every single bond angle are the same. And the bond angle is 109.5 degrees. So for tetrahedral, the bond angle is 109.5. That is how a tetrahedral look like. The number of electron pair is the most important over here, because from this number of electron pair, we will determine what is the basic geometry. Let's go to an example of tetrahedral. The example that I use for tetrahedral, very simple, CH4. Same thing guys, before the basic geometry is your Lewis structure. The first thing about Lewis structure, total valence electron. So your Lewis structure will start off with the central atom and the skeletal structure of CH4. So in this skeletal structure, I have 4 single bond. 4 single bond means 8 electron. So 8 electron, that will cause your total valence electron goes to 0 already. Check the octet or duplet. Your hydrogen right now is duplet, which is already balanced with 2 electron each in the bonding. And your carbon over here is octet. Why is octet? Because you have 8 electron around the carbon. Each bonding is 2 electron. The carbon is surrounded by 4 bonding. So 8 electron. Hydrogen duplet, oxygen octet, this Lewis structure is correct. And when the Lewis structure is correct, what do? We proceed with the calculation of electron pairs for the central atom. Bear that in mind, we only calculate for central atom. And my formula is bonding pair, that we will only take count of sigma plus lone pair. So bonding pair of sigma over here is 4. Sigma, 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 sigma. 4 bonding pair plus 0 lone pair on the central atom, you will have 4. And when the electron pair is 4, guys, your basic geometry will be tetrahedral. Do not spell it wrongly. Make sure the spelling is correct. So that is your basic geometry of tetrahedral. And this Lewis structure right now is wrong because it is not in the correct shape. So you need to redraw this Lewis structure in the shape of tetrahedral. Very simple. Carbon, single bonded to the top, 3 bond at the corner, like that. Okay, so that is how your tetrahedral look like in 2D. You just simply draw it like that, and that is your correct tetrahedral. And what would be the bond angle for tetrahedral? The bond angle for tetrahedral is 109.5 degrees. So every single bond over here is a 109.5 degree. That is for tetrahedral. Next, let's go into the fourth basic geometry, trigonal bipyramidal. What is actually trigonal bipyramidal? The general formula for trigonal bipyramidal, simple, AX5, okay? And the 2D will look something like this. You have your AX2 over here and a triangle in the center. Okay, that is how your AX5 should look like in your trigonal bipyramidal. The number of electron pair, obviously, 5. The molecular geometry in 3D will look something like this. Can you see the difference? Alright, one is in 2D, one is in 3D. So 2D, this is more than acceptable. So we have two types of bond angle over here, slightly different. I have a 90 degree. The 90 degree is over here. Alright, the 90 degree is over here. Another one, I will have 120 degree. I have both of them in this structure. 120 degree is between the triangle. Alright, between the triangle, that is your 120 degree. So you can see over here, in your 3D drawing, you also can see the 90 degree. That is your 90 degree. And that is your 120 degree. Okay, I hope you can see that. Alright, so for trigonal bipyramidal is the only one that we basically having two bond angle in one geometry. I hope this drawing is clear enough to show you why we are having 90 degree and 120 degree. Let's go into an example of trigonal bipyramidal. The example that I have over here is PCl5. Same thing, we'll start off with the Lewis structure, and the first step of Lewis structure, total valence electron. So the total valence electron over here is 40 electron. So the central atom obviously is your phosphorus, bonded to your 5Cl in a single bond. So 5Cl in a single bond, one single bond, 2 electron, we minus 10. I left with 30 electron. The next step is to octet all the terminal atom. So we are going to octet all the terminal atom by giving 3 lone pair to each of the chlorine, because each of the chlorine is already holding one bonding that have 2 electrons. So we are done with the octet of your terminal atom, and we use up how many electrons? We use up all 30 electrons. 6 electrons each of the chlorine. I have 5 chlorine. 6 times 5, 30. We are done. And if you can check over here, your chlorine is now all octet. While for your phosphorus, you have 10 electrons around it. When you have 10 electrons around it, your phosphorus will be expanded octet over here, because your phosphorus is located in period 3. So we are done, and your Lewis structure is right now correct. And from this correct Lewis structure, we need to determine the electron pair. And again, the electron pair, we will only focus at the central atom. My formula remains the same. The bonding pair, which we only take count of sigma, plus the lone pair. And around your central atom over here, I have 5 bonding pair. So the electron pair is 5 plus 0. The electron pair I have is 5. When the electron pair is 5, straight away your basic geometry over here must be trigonal bipyramidal. And how should your trigonal bipyramidal look like? Your trigonal bipyramidal should look something like this. You have your phosphorus, single bond top, single bond bottom, 180 degree like that. And then those in the center must be a triangle. Those in the center must be a triangle. Alright, you can see a triangle in the center. The top and bottom is a linear. So you will have your trigonal bipyramidal form in this drawing. So that is how we draw our trigonal bipyramidal. And in this trigonal bipyramidal, you still put in all your lone pair of the chlorine. And that is how your trigonal bipyramidal should look like in your exam. And if you remember the bond angle for your trigonal bipyramidal, we have 2 bond angle. We have 90 degree and also we have 120 degree. The 90 degree is over here. The 120 degree is over here. Alright, so the triangle, between the triangle, you will have your 120. Between the triangle and the linear, you will have your 90 degree. So that is what we mean by bond angle. The angle between the bond. Okay. Last but not least, the last basic shape that we have is octahedral. So what is about octahedral? Octahedral, again, by this moment, you should know your octahedral will be AX6. The number of electron pair will be 6. And how should your octahedral AX6 look like? Your A in the center, top, bottom linear, and then you are going to have a square in the center. Alright, you are going to have a square in the center. Can you see a square? Alright, so that is how your octahedral look like in a 2D. Okay, linear top and bottom, and then in the center, we are going to have a square. We have another name of octahedral actually. Other than octahedral, we can call it square bipyramidal. Okay, both is correct, both is the same thing. So octahedral or square bipyramidal should look something like this with the number of electron pairs 6. And the 3D drawing of it will be something like this. And from the 3D drawing, you can see over here, the angle that you have is 90. Every bond angle is 90. Alright, because the top and bottom over here will give rise to the 90 degree. And then you have a square in the center. The square in the center will also give rise to a 90. So your bond angle over here is 90. Okay, so let's go for an example of octahedral. I has FS6. Again, we'll start off with drawing the Lewis structure. The correct Lewis structure will be based on the correct total valence electron. So your sulfur as a central atom with 6 fluorine around it in a single bond. So you have 6 fluorine around you for a single bond. That is something like that. Okay, and we minus how many electron over here? 6 single bond will be minus 12 electron. So you will left with 36. And where do we put this 36 electron? We need to octet your terminal first. Every terminal atom will then deserve 3 lone pair because they already have 1 bonding pair with 2 electron. Every single fluorine need another 6 electron. Okay, so all the fluorine right now achieve octet. And 6 electron each, 6 times 6, 36. So I use up all my total valence electron. And we will check whether the Lewis structure is correct or not by looking at the octet of each and every one. Of your fluorine over here is octet because your fluorine all holding 8 electron around them. So your sulfur having 12 electron around them. If you look at it, your sulfur having 2, 4, 6, 8, 10, 12. 12 electron around it means that your sulfur now is in expanded octet. And the problem is, can your sulfur be expanded octet? Yes, because your sulfur is located in period 3, so sulfur can be expanded octet. And from this correct Lewis structure, what are we going to do? We are going to calculate the electron pair with a formula of bonding pair that we will need the count of sigma plus the lone pair. So my bonding pair over here is 6 plus 0. In your central atom, we only focus for your central atom. The bonding pair is 6, 1 bond, 2 bond, 3 bond, 4 bond, 5 bond, 6 bond. 6 bonding pair with no lone pair around the sulfur. With the 6 electron pair, we know that your basic geometry must be octahedral. So how should an octahedral look like? Your octahedral in a 2D should look something like this. As in the center, top and bottom linear. And then the center, we are going to have a square. Okay, can you see a square over here? We are going to have a square. So, top and bottom linear, center is a square. That is your octahedral in your 2D. Put in all your fluorine with their lone pair. And we are done with the drawing of SF6 in octahedral shape. But what would be the bond angle? The bond angle over here is 90 degree only. Every single bond between them will be in 90 degree. If you realize, we've been repeating the same thing, but only the electron pair is changing. So your basic geometry will depend on your electron pair. Your electron pair will depend on the correct Lewis structure. Your Lewis structure will depend on the correct total valence electron. That's why to get the basic geometry, you must first get the correct Lewis structure and the correct total valence electron. As a conclusion, this is the conclusion of your basic geometry over here. We have 5 basic geometries starting with the linear, trigonal planar, tetrahedral, trigonal bipyramidal, and also octahedral. And the main thing that you need to know is the number of electron pair of each and every basic geometry. For the linear, the number of electron pair is 2, trigonal planar is 3, tetrahedral is 4, trigonal bipyramidal is 5, octahedral is 6. Very simple. A bit of tips, alright? That is actually depends on the bonding. So how many bonds you have for the trigonal planar, how many bonds you have for the tetrahedral, that represent the number of electron pair. Simple. Alright, before we end this video, I want to do two more examples that having charge like cation or anion. So let's start off with our anion over here. I have CO3 2-. If your question gives you a CO3 2- and the question asking for the geometry, what would be the geometry of a CO3 2-? Let's see. So what would be your first step? Before Lewis structure, the first step will definitely total valence electron. So carbon over here 4, oxygen over here 6 times 3, because you have 3 oxygen, equals to 18. So the total over here is 22 electron for CO3 only. I have a 2- guy. 2- means you accepted electron. So you accept electron means the charge over here need to plus 2 electron. Because it's an anion, we accepted the electron to become negative charge. So we have extra electron over here. 24 electron. So we'll start off the Lewis structure with the skeletal and also single bond bonded between the carbon and oxygen. So I have 3 single bond over here. I minus 6. I have 18 electron left. So 18 electron left over here, we will octet all your oxygen first. So every oxygen deserves to get a 3 lone pair so that they will have 8 electron around them. So 6 times 3, 18, minus 18, and I'm done with my total valence electron. Don't forget, it's a charge over here. Therefore, for your Lewis structure, you must have a bracket with a 2-. That is how we draw the Lewis structure for cation and anion. Next, before we proceed to the electron pair, we need to make sure that octet first. So oxygen over here is octet. Alright, your oxygen over here is octet, but your carbon over here only having 6 electron. So can your carbon be incomplete octet? We know that incomplete octet in your syllabus is only for beryllium, boron, aluminium. So carbon is not included in incomplete octet. In the other words, carbon must be octet. A bit of tips over here, guys. Carbon must be octet no matter what. So how can carbon be octet when carbon only have 6 electrons around it? Simple. We are going to move the lone pair from any one of the oxygen to become the double bond. Okay? So you are going to have your new Lewis structure over here. Your new Lewis structure will look something like this. Double bond oxygen with only 2 lone pair left. That is your new Lewis structure. Don't forget the charge. So the charge over here is 2-. And you can see over here your carbon right now is octet. Your oxygen remain octet. Your carbon now holding 4 bond. Every bond is 2 electron. So you have 8 electron around the carbon octet. And from that, we are going to work out the electron pair. So your electron pair for the carbon as the central atom will be the bonding, which we only take count of the sigma plus lone pair. So your bonding over here, sigma, 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 pi. Double bond means 1 sigma, 1 pi. So how many sigma we are having around the carbon? We are having 3 sigma around the carbon with no lone pair around the carbon. So 0 lone pair. So electron pair is 3. When the electron pair is 3, what would be the basic geometry? The basic geometry over here will be trigonal planar. So trigonal planar, should your trigonal planar look something like this? This is not a trigonal planar. How should your trigonal planar look like? Your trigonal planar should look like this. Your carbon with a triangle. That is how a trigonal planar look like. So we put in the oxygen back. The oxygen with a single bond deserves to have 6 electrons around it, 3 lone pair. Don't change that. We are only changing the shape, guys. So everything remain unchanged. And over here with 2 lone pair. And remember the charge. Okay, remember the charge. That is your 2 minus. So that is how your trigonal planar look like. And what would be the bond angle? The bond angle over here, 120 degree. So a kind reminder, after you already determine the basic geometry, make sure you redraw your Lewis structure in the correct geometry. You need to show them what do you mean by trigonal planar. Alright, how should a trigonal planar look like? So that is how your trigonal planar look like with your central atom bonded triangle to the oxygen. Okay, that is how your trigonal planar look like. Again, in your electron pair over here, the formula is bonding pair that we only take count of sigma plus lone pair. So the double bond over here having a pi that we will ignore. Okay, we only take count of the sigma, sigma, sigma. That's why the electron pair is 3 only. Make sense? Alright, simple. We still back to the basic of your total valence electron need to be correct, and also your Lewis structure need to be correct before you can proceed to your electron pair and basic geometry. Let's do one more example, and also the last one for today's video, a very simple example, but one of the favorite question, NH4+. Again and again guys, we start off with your total valence electron so that you can proceed with your Lewis structure. I hope by now you already memorized the step. So nitrogen valence electron 5, hydrogen valence electron 1 times 4, give rise to 4. Total valence electron over here is 9, but you're having a positive charge over here, and positive charge happen because you remove electron. So when you remove electron, we need to minus out the electron. So the charge over here is positive 1. We need to minus 1 electron out. That will give rise to 8 electron left for your Lewis structure. So your Lewis structure central atom is N, single bonded to your H in the form of skeletal, and don't forget the charge of your NH4+, that is your charge. And then I have 4 single bond over here, every single bond 2 electron, we minus 8 electron, and we are done with your total valence electron. Check the octet, your hydrogen right now is duplet, so your hydrogen is balanced. Your nitrogen having 8 electron around it, which is octet, also balanced. So your Lewis structure is correct over here. So after your Lewis structure is correct guys, what is the next step? Electron pair. We are going to calculate the electron pair around the central atom. So we are looking at the bonding pair sigma plus lone pair. So the bonding pair sigma around the central atom is 4. 1, 2, 3, 4. So 4 sigma plus 0 lone pair, electron pair is 4. If you remember, electron pair 4 means what? Means that your basic geometry is, what do you think the basic geometry is? The basic geometry will be tetrahedral when the electron pair is 4. And how should a tetrahedral look like? Your tetrahedral is your chicken leg, if you remember. So how your chicken leg should look like? Your nitrogen, 1 at the top, 3 at the bottom, open. So that's how your chicken leg should look like. That is your NH4+, don't forget the charge. Okay, be very careful when it's a charge. Make sure you put the bracket and the charge. And that is how your basic geometry tetrahedral look like. And if you remember as well, the bond angle for the tetrahedral will be 109.5 degree. Makes sense? Alright, simple. So a conclusion for this is, how do we determine the basic geometry? We will start off with the total valence electron. And then you proceed to your correct Lewis structure. Make sure you have your correct Lewis structure. And then we are going to calculate your electron pair. Make sure you calculate the electron pair at the central atom only. And I have given you the formula. Go and check back the formula. From the electron pair, you are going to determine the basic geometry. Okay? From the basic geometry, then you will know the bond angle. That is roughly the flow on how to get the basic geometry. We will start off with total valence electron and correct Lewis structure. Count the electron pair and then you get the basic geometry. That is basically the step to determine the basic geometry. Simple. And in your syllabus, we only have the 5 basic geometries, so don't worry about the rest of them. We only have 5 at this moment. If you are still struggling to draw a correct Lewis structure, make sure you ask help from your lecturer or do drop me a question and I'll try to help you in any way I can. So that's it for this video today. I'll see you in the next video. And don't forget to give me a like and subscribe to my channel. Thank you for watching. I'll see you in the next video.